All right, guys, welcome to another episode of CUDA Education. Today it's going to be a quick one. We are simply investigating the level of detail instructions and how it relates to distance. So let's just run our application to begin the conversation. So we have our application as before, and notice that as we've said previously, for the items that are closest to us, we have maximum level of detail, right? So the vertices and the mesh and all that stuff that's used to make the object, it's high, it's very intricate, it's a lot of instructions, etc., etc. But as we move further away, as you can see here, even with the color coding, the further away you are from the camera, the level of detail changes. So we have this, and then we start to get different lower levels of detail as we move further and further away from the camera. And the reason we do this is because we are trying to save on we're trying to save on on processing power, right? So if the eye can't fully appreciate the detail and stuff, we could save some processing power, save the battery on your mobile device or laptop, etc., etc., by doing just a minimal mock-up of the object, right? So that's kind of what's at play here. And you're gonna notice as I zoom in, you're gonna notice that these guys get green, and then eventually the red disappears, right? Because we're always measuring based on the distance to the camera, how we render the object. So let's go. So we're zooming in, right? And notice as we zoom in that all of these objects, as they get closer, it changes color and there's more detail, okay? And notice that now we don't even have the red anymore because we're almost to the end of the the number of objects, right? So notice that as we get all the way to the end, that these also turn green, right? And then as we go back further, so these objects are green now, but as we go back further, they lose levels of detail again, right? And then of course we have our red as before. Okay, so what we're going to do also is now I'm going to freeze the frustum, right? I'm going to freeze the frustum so that now everything stays the same. So as I zoom in and out, the level of detail stays the same. That way we could actually see what is going on. So now we're going to zoom in, but the frustum is frozen, which is the world space and the view and all the processing for the distance to the camera. Everything is frozen, but I could still zoom in and out of the scene to see what's going on. So when I zoom in now, we're going to see we have our greens here, but then we have, a change in color. Notice that it's less detail. It's a little bit less detail. As we go further and further, we get another change in color, less detail. You could definitely see it around the eye and even the mouth, right? Less detail again. As we go further and further, we have even less detail again. So we have this, and then we have this, less detail. As we go further, we have even less detail, right? The lowest level of detail as as we're allowed, right? So I guess it's what? I think it's 5 levels of detail. 1, 2, 3, 4, 5. Right, so 5 levels of detail, okay? So that is, and of course, if we unfreeze the frustum, now we're going to be processing the distance to the camera, and we're going to be making changes accordingly, right? So even if I go here, and then I unfreeze, we're going to now take into account distance of the camera, and then we should, the levels of detail should change, because now, the level of detail is based on the distance to the camera, but it's frozen now, but then when I unfreeze, it should adjust accordingly. as it does, right? So now the level of detail is back to what it was before. All right, so that's pretty much that. What I wanted to do is just quickly go over what's happening in order to make that happen. So if we go to our main function, so we're in the cull shader, right? So we're in the cull shader. So remember, we have the source code and then we have our shader. Shaders live on the GPU. So we have our cull shader, right? And we definitely do our Frustrum check, right? To figure out, you know, basically when we freeze, you know, what things to include and what things not to include. I'll just quickly go over that real quick for those that maybe jumped to this video and didn't. So as you can see, left to right, up and down, we have objects everywhere. But if I freeze a frustum, which means I'm culling things that are not visibly viewable in the current frame of the camera. If I freeze the frustrum now, you're gonna see that for everything else that was outside of the view, the objects have been culled, right? And if I unfreeze, then the objects reappear again, right? So if I freeze, the objects disappear. And if I unfreeze, they reappear, right? We could even do it so when I freeze, right, the objects disappear, but then when I unfreeze, they reappear again, right? So that's what this function was, and the previous video talked about this specifically. And specifically, it talked about this function, which was this guy up here. This is a function called from main, and specifically this equation. And we went into the equation, and I suggested some other YouTube videos for you guys to watch. But basically, we test against this equation, which deals with the plane, deals with the object itself and the radius, the sphere, imaginary sphere around the object, and then we test against the plane, which I'm not going to go through here again. But what I wanted to discuss was we do the frustrum check, and then we also have to decide. So we do some draw calls, which I'm not getting into in this video, but we do the frustum check, but then we have to decide the LOD logic, and that's where this guy comes in, right? So specifically just here, I'm not dealing with the draw calls. You know, obviously we update the statistics, and we know that we update the statistics because as we zoom in, you notice that the level of detail changes. The calculations change, right? So notice that, so we have the red, which is level 5, 32,000. As we get closer and closer, notice that the red slowly disappears, right? To the point of falling to 0, right? We have a little bit of red at the end, but then it falls to 0 because no object is too far away from the camera. But as we zoom back out, notice that the the LOD objects increase dramatically. And if we zoom all the way out, everything basically falls to level 5 detail, which makes sense, okay? So we do update the statistics, and that's this guy right here, right? And, you know, really and truly, if we were to comment this out, it wouldn't be updated, but we're not worried about that. What I wanted to just kind of go over is select appropriate level of detail level based on distance to camera. So this is our test now to find out what is the level of detail that we render the object in, okay? So I don't want to dive too much into the mechanics of it, but I just wanted to highlight the function. So we have LOD level, max LOD level, right? So I guess the max is 5. I guess, yeah, right, 5, right? So we basically go through all of the level of details, right? And each of the level of details has a distance associated with it, which makes sense because when we go into the object, you know, for things that are really close to the camera, the distance, the LODI is, you know, I guess the LODI is very low, right? So for a distance that's right, so you know, basically the distance is low, but as the object that being rendered for consideration for being rendered is farther away, we you know, the equation basically changes. So so yeah, this I don't really want to get into the actual test. I mean the mathematical test, but you could see here, this is the equation. So we're doing a distance calculation, right? We're doing a distance calculation based on the position of the instance, the position of the object, and the position of the camera, right? And we're saying, what is the distance between the position of the object and the position of the camera? And based on that test, based on that test, we assign the level of detail to the object, right? So we do LOD level I equals I. So then we do basically index draw first index equals LODS LOD level first index LOD level index thing. And I believe this is what is basically driving, you know, what the level of detail is for the object, right? So based on what is assigned here, we get this. Now, you know, as soon as we get a level of detail that actually passes this if test, we basically assign that level of detail and then we break the for loop, right? So this right here is a for loop, and we're basically going through the for loop based on each of the, you know, so I guess it would be 0, 1, 2, 3, 4, 5, right? 0, 1, 2, 3, 4, 5, right? So maybe there's, I guess, 6 levels of detail. 1, 2, 4, 5. But right, but so we're basically looping through each one of them. As soon as one of them passes this test, we assign that level of detail and then we break out of the for loop, right? And then we use these guys to basically associate that object with that level of detail, and we push it to the draw call, which I need to investigate some more. So I don't really want to speak on the indirect draws and all this stuff, because this is a whole nother cup of tea, which I don't want to discuss right now. But just know that we assign a level of detail to the object based on the distance between the camera and the instance, or the object instance, right? And then we basically do the draw call associated with the appropriate level of detail, right? And that's pretty much it. We update the statistics. Obviously, if we don't pass the, because this is the if it passes, and this is the portion if it fails. So obviously, if it doesn't pass the Frustrum check, which basically means we're not rendering the the object. If we're not rendering the object, then obviously we just bypass all of this stuff and we don't even draw the object, right? So that's what this is right here. That is pretty much it. Okay, so if I simply disable the stats, right? So I'm gonna remember I'm in a shader, so I have to compile the shaders to SPARE-V format, and then so if I disable the stats and I rerun our application, so right now it adjusts based on what's actually happening. But if I disable the stats and then I rerun the application, what will happen now, I'm assuming, is that nothing happens, right? So the stats, the LOD stats basically don't update, right? Which makes sense because our GPU, the shader on the GPU is not updating the statistics based on what we processed here with all of the instructions, right? So if I have to recompile, if I put back in the stats and I rerun the application, I will get back my LOD information, right? And that's GPU programming for you guys. That is GPU programming. Not too hard, right? Not too hard. Not too hard. But yeah, guys. So we have a little bit of understanding of how this LOD, level of detail stuff works. Pretty cool stuff. You know, what the big elephant in the room and the big thing that I have to tackle is the whole indirect draw, the indirect draw conversation, and it's not as easy and straightforward thing. There are a lot of things going on between what's happening on the CPU side and then what's, you know, buffers and struts and stuff, and then, you know, these shaders on the GPU side. So we have a cull shader, an indirect draw fragment shader, and an indirect draw vertex shader. A lot of things are happening. You know, a lot of things are happening. You know, even the cull shader is like, a lot of things are happening, which I have to dive into. I'm probably going to do it piece by piece, but we shall get through it. But yeah, and then, you know, of course we have our source code on the CPU side that's like organizing everything, and we are on the CPU side, we are about 800 lines of code deep. Okay, some stuff like this render function is familiar to us, but we will need to dive into that in another video. Thank you guys for watching. This is CUDA Education. If you want to run Vulkan on your machine, on your Windows-based machine, you need to get tutorial number 1 to install the Vulkan SDK, and tutorial number 13 to install all of these examples, right? Now, I assume a Windows-based machine with a Vulkan-capable GPU. If you want to run the ray tracing stuff, this is not a ray tracing example, so don't worry if your GPU is not ray tracing capable, you will still be able to run the example. But for those that want to dive into the ray tracing series, I have videos freely available on YouTube talking about the ray tracing stuff. You will need to make sure your GPU is also ray tracing capable. Okay, for NVIDIA, that's RTX and above. For Intel and AMD, you'll have to research that for yourself, right? But that's tutorial number 1 for the Vulkan SDK and tutorial number 13 for all of these examples. I am now right here, right? So we've kind of, you know, I'm just going through all of the examples, and you know, we have, for this example, we have 3 shaders, and of course 1 source file on the CPU side, right? And we are working our way through. Thank you guys for watching. Like, subscribe, tell your friends, work on this stuff together in a group. It's more fun that way, and keep it moving. Have a great day. Bye.